So we're going to do an example problem using the principle of conservation of momentum, and that principle can often be applied to collisions, which is the example that we're going to look at right now. So when we use the principle of conservation of momentum, we're going to be comparing the initial and final situations for some objects, and I've represented that here. I have two fish, a big fish B and a little fish L, and the initial situation shows that they are approaching each other with some initial velocities, and the final situation in this problem is going to be the big fish has eaten the little fish, and the goal of the problem is going to be to find what is the final velocity of the fish. Now, because the big fish ate the little fish, they're kind of stuck together, so they have the same final velocity in this problem. So let's assume we know some numbers about these two fish. The mass of the big fish, we're going to say, is 12 kilograms. The mass of the little fish, we're going to say, is 4 kilograms. And we're going to say we know their initial velocities. Now, on my picture, I need to add something really important. Just like velocity is a vector, momentum is also a vector. It can be positive, it can be negative, because it has a direction. So we need to indicate our positive direction. It doesn't matter which way we choose it. I'm going to make positive to the right. So the initial velocity of the big fish is going to be positive 2 meters per second. The little fish, who's moving to the left, well, that's the negative direction, so I need to make sure the velocity is negative. V initial left is going to be negative 10 meters per second. Okay, before we do the conservation of momentum principle, let's make sure we have proved that conservation of momentum actually applies in this situation. So we have learned that the total momentum of an isolated system is conserved, and so we have to define our system to make sure we explain that. So the system is big fish plus little fish. And we need to also think about the force diagram to prove that this is an isolated system. So we need to represent the external forces acting on this system during the collision, which is really all we're interested in. And so we would say, I guess they're underwater, so the water is holding them up. I'm just going to call that N of
G. And since there's two fish, I'll go ahead and put 2 mg's. There's the weight of the big fish. There's the weight of the little fish. The water is holding up the big fish. The water is holding up the little fish. Now, those forces, if it's an isolated system, need to add up to 0. So we're just going to make the statement. We're going to assume that these are all in balance and that the net external force on our system of A plus B is equal to 0. Okay? Therefore, the total momentum of A and B initial must equal to the total momentum of A and B final. And we can prove that with our Newton's second law, just for completeness. That's because, as we've learned, the net force on any system times the time that that force acts is equal to the change in momentum. And if the net force is 0, then the momentum can't change. Okay, so we proved that
the momentum of our system is conserved. Now, the goal is to find the final velocity of the system, so we're going to write our conservation of momentum equation to solve for that. So the easiest way to do that is say momentum initial total equals momentum final total. Momentum is the product of mass and velocity. So I would say mass of the big fish, v big fish initial, plus mass of the little fish, v little fish initial. That's the total momentum before the collision, equal to mass big fish v big fish final, plus mass little fish v little fish final. That's the total momentum after the collision. Now I can make this a little bit simpler. Since they're stuck together, the big fish is going to eat the little fish. We're just going to say that both of these final velocities are equal. So I can just factor out that v final and make it mass big plus mass little times v final. Okay? Same thing here on the left side. If I want to solve for v final, I just divide both sides by mb plus ml. I get m big v big initial plus m little v little initial over m big plus m little. And I'll put in the numbers from the other page. The mass of the big fish, 12 kilograms. V initial, 2 meters per second. Plus mass of the little fish, which we said was 4 kilograms. V little initial is negative 10 meters per second. All that divided by 12 kilograms plus 4 kilograms. And so that's 12 times 2 is 24, plus 4 times negative 10, which is negative 40. So that's negative 16 kilograms times meters per second in the numerator. Negative 16 kilogram meters per second. In the denominator, I have 16 kilograms. Kilograms cancel out, so I get the final velocity is negative 1 meter per second. And you can think about what that means. Because the final velocity is negative in this example, the system is actually moving in the negative direction, which means that big fish, which ate the little fish, now is moving backwards. Basically, the little fish, if you look at the data, the little fish had a greater amount of momentum than the big fish had. Okay? And so the net effect of that collision was that the total momentum of the two combined was the same in the beginning and the end, but the total momentum is therefore a negative amount, right? Because they're moving in the negative direction. So this was an example of how to use the principle of conservation of momentum in a completely inelastic collision.